video for the second part of the chapter 19 lecture. We're going to be looking a lot more at thermodynamic processes and how they look on PV diagrams. So, constant volume, we have a name for that. It's called isochoric process. In that, we usually have a container. You'll see wording in the problem that will mention it's a sealed container, or maybe just directly tell you it's an isochoric process. And on a PV diagram, that's moving directly up on a PV diagram. The pressure will go up in a situation like that because the volume is constant. There's nowhere for the gas to go. And of course, the temperature is going to heat. Temperature is going to go up too in this process. And we are inputting heat into it. Thing about this is no work's being done, right? You can't have work if you don't have a volume change. So let's get right to a problem. We have a constant volume gas thermometer placed in contact with a reference cell containing water at the trouble point. After reaching equilibrium, the gas pressure is recorded at 55.78 kilopascals. The thermometer is then placed in contact with a sample of unknown temperature. We have a new pressure here. Let's look at how this one is done. So in a constant volume process, the number of moles, right, are the same, and the volume is the same. So you can create a proportion that's pressure to temperature. So as you can see in the bottom right here, I have that proportion, pressure to temperature. Just be mindful when you do this to have the right units for your temperature. If it's not a delta T, gotta go with Kelvin, so we gotta make sure we convert this to Kelvin. So I got 273.16 as my 0.01 Celsius temperature. I'll take my ratio of pressures here. We end up with this new temperature. I'll convert it back to Celsius. And so this thermometer is, based on the reading pressures, is able to determine that the sample is 45.75 Celsius. Okay, let's get back. All right, so we want to try to identify what process is going on here. A cylinder of gas has frictionless but tightly sealed piston of mass M. Small flame heats a cylinder, causing the piston to slowly move upward. What kind of process is this? So think about this for a minute. The answer is isobaric. So it's not an isochoric process because the volume is changing, right? It's not an adiabatic process because we are adding heat to the gas here, so that's not adiabatic. And it's certainly not isothermal because if you're going to heat something up, well, that's it, you're heating it up, right? So why is it isobaric? How do we know that the pressure is going to be the same? Well, in an isobaric process, the pressure, in this here, where we don't have a sealed container, we actually have a container that's open to the atmosphere. And the idea is that if you look at, let's say, that piston that lies on top, you have the weight of the piston pushing down, and you have atmospheric pressure pushing down. And at any given moment, that's going to be basically balanced. I mean, this process is what we call that quasi-stellar process. And so at any given step, we're effectively in an equilibrium here. But if you look at the pressure that's being exerted on that gas there, it's due to atmosphere and the weight of the piston. It's not really due to any other factors here. And so as you heat this up, those things have not changed, right? Those things have not changed. So this is a good example of how to do an isobaric process. On a PV diagram, we'd be moving directly to the right. The sample is going to heat up, and there is work being done, right? So, all right, so cylinder of gas has a frictionless but tightly sealed piston of mass M. Gas temperature is increased. What's the final to initial volume ratio? Okay, so think about this for a minute. The answer is B. So just like in the previous example, the isochoric example, an isobaric example has, well, we're going to have the number of moles. That's not going to change. Nothing is indicating that we're losing or adding gas here. and the pressure is the same, so you can also create a ratio of volumes to temperatures. You got to make sure, again, that those temperatures are in Kelvin. And when you do that, we see that we get a ratio of 1.33. Okay. Fantastic. All right, let's do another example here. I'll bring up my slide for this. So we got two cylinders here. They're gas with same temperature, but the volume of the first gas is a bit larger. So we got to figure out why that would be. They both have the same piston on top, and we want to see how the pressure of gas 2 is going to compare to that of gas 1. Well, as I just explained, even though they have different volumes, they clearly, they don't have different pressures. The pressure, again, is due to the atmosphere and the weight of the piston, and that is identical in both situations, so the pressure must be the same. Okay, well, if the temperature, all right, is the same and the pressure is the same and the volume is larger, well, it must mean that the amount of gas is different, and that's why the volume is bigger. So we'd see that the number of moles in gas 1 is going to be larger. We want to heat up gas 2, and we want to see what happens to pressure and the volume there. Again, pressure is not going to change, so that answers that question. So for gas 2, we have the same pressure when we heat it, same pressure, right? Same amount of gas. So we do our ratio of volume to temperature, as you can see down here, change things to Kelvin. We get a 1.2 for the increase in volume as it heats up. We got a cylinder of gas floats in a large tank of water. Frictionless but tightly sealed piston of mass M. Small masses are slowly placed on top of the piston, cause it to move slowly downward. So what kind of process would this be? Just think about this for a moment. The answer here is C, an isothermal process. Okay, let's go through the options. Well, the volume's changing, right? So not isochoric. We're add masses to the top. That's increasing our pressure, so it's not B. The fact that it is in this giant tank of water means that any heat that might be any work that's being done on this gas, that heat is coming out. And the idea with the bath is that it can maintain the temperature because you're basically sending out heat to a very large amount of water out there. And so there's definitely a heat flow, but this setup allows the temperature to remain the same. So let's start looking at isothermal processes. So on a PV diagram, that is basically like a 1 over x curve. You can see the ideal gas law right here. Oops. The ideal gas law. Oh, I got a new pen. This is difficult to use. But anyway, you see the ideal gas law there. And that's everything on the numerator, nRT, is a constant. So you have a graph that's just 1 over x. And that constant can differ, obviously, for different amounts of gas or different temperatures. And you create what we call isotherms. So there are basically different kind of slope to those lines. And the rule is the temperature increases as you get to higher and higher isotherms. So when you think about the process on the HR diagram, anything that takes you right or up is going to give you increased temperatures because you're going, to the upper diagonal there. All right, so question for you here is isothermal expansion of ideal gas, the amount of heat that flows into the gas, what? Think about this for a minute. The answer here is B. So if this is an isothermal process, right, that means your E thermal. So if we look at the first law of thermodynamics, E thermal, right, that's 0. But first law of thermodynamics says that's also Q minus W. So it means the heat and the work have to be the same. And that's why this is. Okay, gas follows the process shown. What's the final to initial temperature? All right, so the answer here is C. So for this process here, it's not really a process that's one we've identified, but we can use our relationships, our ideal gas law relationships. So when we deal with something on a PV diagram, one thing that's got to remember is that this is always under the assumption that the amount of gas doesn't change. It's very difficult to try to display how that would look on a two-dimensional PV diagram. It would be very hard to see, actually. So in this example here, we can create ratios in the ideal gas law, and we can simply compare final pressure to final volume to see what's going on here. So in the case here, the volume goes up by a factor of 2, the pressure goes up by a factor of 4 here. So overall, we are increasing in our temperature. Both things would increase the temperature, actually. So you can base it purely on that idea because you're going up to a different new isotherm up there. So the answer here is C. For sure. All right. Ooh, this one's good. All right, example 3, we got a gas at 2 atmospheres of pressure and a temperature of 200 Celsius. We go on an isotherm where we double our volume. Then we go through an isobaric compression until we get back to the original volume. And well, the process is already shown on the HR diagram. I've displayed it here. Now we want to figure out what's happening with the temperature and pressure through the process here. So let's go ahead and work that example. Let's just, okay. So path 1 to 2 is an isothermal process. And an isothermal process, what we have here is we have this nice relationship that can relate the final and initial quantities right here. Okay, I can't annotate this, huh? There's got to be some way to do that. We'll figure this out later eventually. And so if the volume is going to increase by a factor of 2, the pressure is going to have to drop by a factor of 2. So we get down to 1 atmosphere. We have an isobaric process now. So the pressure is the same. And again, with the ideal gas law, we can create a proportion that compares initial to final for volume and temperature. And so we solve for that final temperature. And remember, everything's got to be in Kelvin when you use the ideal gas law. So we'll convert the 200 to Kelvin. And then I'll convert it back to Celsius. So it's negative 36.5 down here. And the reason why I'm converting it back to Celsius is it's kind of like physics etiquette, I guess. You know, if you're given units to start off a problem, even though those may not be the units that you will actually do your calculations with, it's generally a good idea to return information back in the language it was given to you. So it's not 100% necessary, but it's be a good person about that. All those bad people out there not returning the right units, you know. All right, so now we're going to look a little more carefully at the internal energy of an ideal gas. So, internal energy was something that we've kind of talked about throughout physics here. This first comes up way back when we talk about friction. And we looked at energy conservation, right? And what we say is that when energy is dissipated in friction, it just turns to E thermal. It just kind of goes away, right? Well, we're going to look more detail at that now. We've done this a little bit so far, but let's get really into it now. The internal energy of an ideal gas is temperature dependent purely. That's it. And we actually saw in the previous chapter a couple different expressions. We worked out a sort of average kinetic energy that was based on temperature, and we worked a collective kinetic energy. And that collective kinetic energy is what we equated eventually with the internal energy of an ideal gas. So in this example here, it may seem strange, but if we have a vacuum sealed
compartment in this container and we break the partition, then the gas will expand. But the temperature will not change here because if this is insulated, nothing's coming in, nothing's coming out. Overall, the temperature really can't change. That the energy of the particles are going to remain the same. I mean, again, relate this back to kinetic energy, right? It's the amount of the kinetic energy the particles going to change just because they can explore a larger region. No, I mean, volume's going to increase. So what? Pressure drops? Yeah, that's true. Because if you think about our original definition of pressure, we talked about it, things bouncing off the walls of the container in a given interval of time. Well, now we've got a bigger volume, so they travel farther and they're going to hit less frequently. So that makes sense that the pressure is going to be a bit lower here. So we're going to be describing a lot of gases in terms of their molar heat capacity. So this was an idea that we first talked about in the very first lecture. We did it for solids and liquids. We have to develop some ideas of gases before you're able to introduce that for a gas. But we looked at a really simple gas when we did our kinetic theory calculations, and we came up with a 3/2 nRT. And that was the heat capacity, basically, of that gas. Now, we label it like this, capital CV, molar heat capacity. The C means constant volume. Now, this is a tricky phrase here. When we say constant volume, what we really mean to say here is there's no work being done, okay? There's no work being done. You'll see a lot of things they'll say like the heat capacity at constant pressure, and that's when work is being done. However, what's tricky about that is sometimes the pressure isn't always constant necessarily. It's better to speak about these two values as being, is there work or there is no work? So in the constant volume process, obviously there's no work being done. So that's simple enough. And we'll talk about constant pressure process a little bit later here. So anyway, to measure this, we raise the temperature of an ideal gas in a container that has a constant volume. We don't worry about thermal expansion or anything like that. And when we add heat to that, the temperature is going to go up a certain amount. And obviously that's related to the ability of the gas to, absorb that heat and increase in its temperature. Okay. The constant pressure process is here. In this example, there's work being done. So when work is being done, there is more energy needed to be added because you have to heat up the gas and you have to move this piston if the piston is going to be going up here. So it's not a constant volume process. This is a process that involves work. So our value for CP will be larger. You need more energy to increase to the same temperature because now some of the energy is being put towards work. All right? All right, so there is going to be a relationship between these two quantities here. And because we already have relationships between heat and work in the first law of thermodynamics, so it makes sense that there would be a relationship between these quantities here. So you're going to need more heat at constant pressure than at constant volume. Ultimately, though, in these processes here, if we're going to produce the same temperature change, we are, going about this in a couple ways. So one way we can do it, and you see in the process down here, is the constant volume process goes straight up, right? The pressure increases, no work's being done, and the amount of heat that's needed is equal to the change in thermal energy. Great. Now, if we then look at the constant pressure process instead, what happens is, yes, the temperature goes up to the same value as before, but there was work being done. And according to our first law of thermodynamics, that amount of heat is going to be the change in thermal energy plus the amount of work that's being done. So ultimately, what we're saying here is that the delta U's are the same here. If the delta U's are the same, we can equate these things. And for Q, we're going to be using these quantities here, the NCP delta T, NCV delta T, and the work that's being done here we can sort of rearrange those quantities, right? Because look, if we have, if our work for a constant pressure process is P delta V, well, using the ideal gas law, that's N R delta T, right? And for, the relationship that we have up here, if we want to figure out what that's going to be, it's going to be NCP delta T. That's the heat that was done in the constant pressure process, this quantity right over here. Oops. And the one up here, I just got this thing and it's difficult to use. All right. So if we go down here, well, this is very hard to use. Oh my goodness. Plus NCV delta T, and that's equal to the nRT. You drop the n's out, you drop the delta t's out, and then we end up with this relationship right up here. Okay, this shouldn't have been a plus. This is because look over here. What I'm doing is I'm equating these relationships here. So this is the constant process, volume process. Down here is the constant pressure process. So there's not a plus here. It's on the other side. Anyway, so this should be the equal sign here. My goodness, it's hard. It's hard. So this is the equal sign, not this thing. Okay, and I don't this pen. I swear. All right. Anyway, I'll figure it out. Okay, so as you can see here, these are our measured molar specific heats, and surprise, surprise, the difference between them is a factor of R. Now, monatomic gases follow this very nicely. This is the values that we expect. Diatomic gases are a bit higher because there's more going on with a diatomic gas. So, did we talk about this? I don't remember we talked about this, but these are the ideas of the degrees of freedom, which I can't remember if we talked about it or not. So if I did talk about it, well, you already know, but if I didn't talk about it, I guess we talk about it later in this lecture here. But the idea is that diatomic gases have more degrees of freedom. I'm pretty sure we talked about this already, because you guys did homework about this. Yeah, we already did the degrees of freedom. So anyway, with the diatomic gases, the degrees of freedom are higher. So the heat capacity is higher because when you put energy into it, there's energy going into various modes. And for diatomic gases, there is a sort of rotational aspect that is a factor. And then if you get really hot, there's a vibrational factor that goes into effect. And anyway. All right, so a question for you here. Ideal gas begins in the thermodynamic state A. When the temperature of the gas is raised from T1 to T2 at constant volume, heat flows into the gas. The same gas begins in a state A, has temperature raised, constant pressure. The amount of heat that flows into the gas is what? The answer here is A. Right, we already talked about this, right? So, yeah, you need more heat because you're going up to the same temperature, but you're also performing work. So you need more energy. All right. A mole of air has an initial temperature of 20 Celsius. 20 joules of heat energy are transferred to the air in an isochoric process, and then 20 joules are removed in an isobaric process. Afterward, the air temperature is what? Answer here is greater than 20. Okay, so the reason for this is that in your isochoric process, no work's being done. So you transfer that heat, temperature goes up, right? And then when you remove that in the isobaric process, remember some work's being put to energy. So this is not the same 20 joules in terms of what they're doing. Sorry, 200 joules. The 200 joules, some of that's being done are being done in terms of work. So in reality, you probably only have 180, 170 for the temperature change or whatever it is. So we're not going to be able to get back down to the same temperature, right? So, okay. Did I hammer that into you enough already? All right. So we have this quantity gamma here. It's going to show up in the adiabatic processes that we're going to talk about in a moment here. And the gamma is a ratio of heat capacities. And again, it's helpful when we start solving our adiabatic problems here They have set values for gamma here. For monatomic gases, it's going to be it's 5/3 or 1.67, and for the diatomic gas, this one is going to be 1.4, and that's like what, 7/5, right? So that's 7/5. The other one is 5/3, and this corresponds again to those degrees of freedom we talked about before, and that's why we have these different values. So one thing you got to be mindful of, and you sort of saw this in the first exam and the exam that's coming up, you'll have the same idea, is that you sort of have to be aware of what's monatomic, diatomic, and you won't necessarily always be told that. You know, if it's air, that's diatomic. If it's nitrogen, it's diatomic. If it's oxygen, it's diatomic. If it's helium, it's monatomic. You know, if it's hydrogen, it's diatomic. Those are things that we gotta, and we do all these things enough that hopefully that will be familiar to you. Now, if I throw some weird gas at you, I won't expect you to know some obscure gas, you know, what that is. So, all right, another example here. Let's check out example number 4 here. We got 3 moles of O2 gas, diatomic. All right, 20C, we have 600 joules of heat energy to transfer the gas at constant pressure. Then 600 joules are removed at constant volume. We want to know what our final temperature is. We want to show the process on a PV diagram. Okay, so we are going to have 3 isotherms. We have our one at 20. Then as we have the constant pressure process, we're moving directly to the right. So that's going to result in a higher temperature, and then we're going to drop in a constant volume process. That will result in an even lower temperature than we had before. And again, it has to do with, was there work being done before or afterwards? There was work being done before, so the amount of increase in temperature couldn't have been as much because some of the energy was being put towards work. Now, in a constant volume process, we don't have that, so we can drop down to an even lower temperature for the same amount of heat transfer. So we have our CV and CP values for our O2 gas, which is given right here. And we just go ahead and calculate these values of Q, because they have the delta T in it. So for the constant pressure process, our Q is NCP delta T, and for constant volume, it's QNCV delta T. And so for the first process here, we're going to put in our 600 joules. We have 3 moles, right? Yes. And so the delta T value is 6.87. So we increase, right? Increase in that. And so that's our 26.8 mark here on our PV diagram. And then we have our constant volume process where we're going to drop. Now that would actually be there probably should be a negative sign here because that is heat that's being taken out of this, or you could flip around the delta T. But here, again, yeah, that should be a negative in front there to indicate that, you know, we are taking energy out. It says removed, right? So I can't do that on the PDF yet. Anyway, we drop about 9.6, so we get down to our final temperature of 17.3. So overall, we had a drop at about almost 3 Celsius as a result of these 2 processes here. All right, so I hope I hammered the constant pressure, constant volume process. Now, the thing with the constant volume process, I want to say one thing about this. The Q value, so these are for Qs, just to be really super clear about this stuff. These are things we use as specific heats for Q, right? For Q. The NCV delta T can be used to characterize any thermodynamic process when you want to talk about the change in internal energy, okay? So there's a big difference between these statements here and if they're being used for Q or are they being used for the internal energy. Because if it's talking about Q, constant pressure, constant volume is going to look like this. When it comes to any thermodynamic process and we look at the change in the internal energy, okay, then NCV delta T can be used for any change in internal energy. Okay, so I mean that just really comes from the fact that if you look at Well, I mean, it doesn't matter if there's work being done or not. This is, I guess my point is this. These are statements for Q. When you go outside of Q and you look at internal energy, we stick with the NCV delta T. That always works. And that goes way back to our kinetic theory stuff and what we worked out there in terms of the collective kinetic energy. We derived that a while ago. What chapter would that have been? I don't remember what chapter that is now. All right. Let's get back to the slides. I don't think I have another. Oh, no. All right. So here, we got a typical dorm room or bedroom contains about 2,500 moles of air. Find the change in internal energy of this air when it's cooled from blank to blank at a constant pressure. Okay, so change in internal energy. This is what I was talking about before. The change in internal energy, we're not talking about Q here, we're talking about change in internal energy. So for the change in internal energy, you can use NCV delta T. The volume of this room is constant, therefore there's no work being done. Yes, it's a constant pressure process, but it's also a constant volume process as well. In fact, what's different about this is that the number of moles in the air has got to change. Right? If you have constant pressure, you have constant volume, and your temperature's changing, well, what's changed? Well, there's air going in and out of the room. Okay, so it's not a sealed room, but it is a constant volume room, which is what houses do. Houses have exchange rates for their air, which is mostly a good thing to have. All right. So we're going to use our NCV delta T. Again, there's no Q here. It's delta E. Big difference. Diatomic gas, we use a value of 1.4 for our gamma here. So that means our CV, well, the 1.4 informs us that we have diatomic. We already know that though, right? Because it's air. Air is diatomic. So the CV value you're going to use is 20.8. Put everything into the equation here. And you have to remove 4.7 times 10 to the 5th joules of energy to drop that temperature down. All right. So big thing about this again. Change internal energy, NCV delta T. Even though it's a constant pressure process, we're talking about heat. Okay, heat is when you use the CP stuff, not for internal energy. Let's get back to it. All right, last topic here is adiabatic process. So, adiabatic process, Q is 0. The change in internal energy is equal to minus work. So the PV diagram illustrates this really nicely. This looks a lot like an isotherm, but we are actually generally dropping, well, if we're increasing a volume, we're dropping to a lower isotherm. So if there's no heat transfer here, the increase in the volume is going to result in a drop in the temperature. Okay, there is work being done because the volume is changing, but it is always steeper than the isotherm. So adiabatic processes are kind of nice to work with because that Q is 0, and then your first law of thermodynamics becomes a little bit simpler to work with. Right. Question for you here. Ideal gas is taken on in the cycle in the PV diagram. So we go at A, C to B, back to A. So it's a cyclic process. Process CB is adiabatic. Oh, that's nice. For process CB, what's happening here? Well, think about this for a moment. The answer here is D. What changed? My arrows changed slightly. Weird. All right, so it's an adiabatic process. So A, B, and E are wrong. That's it. A, B, and E are wrong. And then for CB, we're going backwards, aren't we? Our volume is dropping, so the work is negative. That's it. I mean, I look at Q 0, and the work is negative, and I know it's D. Now, what about internal energy going up? Yeah, if you go backwards in the isotherm, you do increase your temperature, right? Because the volume is dropping in that case. All right. When an ideal gas is allowed to expand isothermally, the gas's amount of work equal to 1, 2. The same gas is allowed to expand adiabatically. What amount of work is being done? The answer here is less. This is just based on this picture right here. If we were on an isotherm, we'd be up a little bit higher. There'd be more area bounded by the PV curve here. But the adiabat takes us to a lower location. Less work is being done. Fantastic. Okay. So now the relationships at the top here. These relationships are based on looking at the first law of thermodynamics. We look that our change in internal energy is equal to minus W. In your textbook, this would be section 19.8 in the OpenStax textbook. If you prefer that or use that or whatever, or you just don't want to spend X amount of dollars on a textbook, let me find exactly what chapter that would be for you. Let's see, table of contents. Where's my thermo? Where's my thermo? What volume has thermo in it? That's chapter 2. This is section 3.6, adiabatic process. They go through the exact same derivation on how to get this right here, this relationship. There is a PV relationship. There is also a PT relationship and a TV relationship. The PV relationship is what is derived in your textbook. The other ones are derived simply by looking at ideal gas law relationships. So it's pretty much the same thing. And the gammas are exponents here. And again, be mindful of what those values are. So, again, I'm not going to spend a ton of time just deriving these equations. You can read them just as easily as I could derive them for you. In fact, I think there's some value in reading the more worked out, developed solution in your textbook. Of course, if you have any questions about that, then please let me know. But it's a little bit of calculus and algebra, nothing too bad though. All right, so we have a gas in a container expands rapidly, pushing the piston out, temperature of the gas. What happens? The answer here is C, it falls. Why? This is an adiabatic process. How do I know that? The word rapidly. Where's my little clicker thing? I lost it. There it is. I can't even see it. Oh, it's way up here, a little tiny. Rapidly. So, gas in a container expands, volume increase rapidly. Well, I'm telling you now, that's the word for adiabatic. Rapidly. When a thermodynamic process happens very quickly, you don't have time for heat to go in and out. It's inherently an adiabatic process. Of course, that's not perfect, but the approximation is very, very well. And if it's an adiabat and your volume's going up, well, we know the temperature drops. So that was something that you didn't realize maybe at first, but now you do. Adiabatic means, well, no, let me put it this way. Rapidly always means adiabatic, not the other way around. Right? Adiabatic is not necessarily fast. It can, it doesn't have to be fast, but if it is fast, it's adiabatic. Okay, gas in a container expands rapidly, pushing the piston out. Temperature of the gas falls because what's exactly going on here? The answer here is D. All right, heat energy is removed. Well, it's not C. This is adiabatic. Density of the gas falls. Well, that has nothing to do with anything, right? When density of the gas falls, so what? Gas pressure falls. That's not happening. Remember, these things don't do that. So it's work that's being done. That's really what's going on here. So, all right, let's do our example here, example 5. We'll discard my annotations here, and we only got 2 more to do, and we're done here. Let's look at it. Ooh, look it up. There's a lot of things on this slide. That means it's good. All right, let me full screen this thing. All right, gasoline, air containing gasoline vapor is emitted to the cylinder of an internal combustion engine at 1 atmosphere and temperature 30 Celsius. That's nice. The piston rapidly compresses the gas to 10 times its original volume. So I know I have numbers in there, 550, but the word rapidly just popped up. So we know what we're doing here. This is going to be adiabatic. And I don't really need my volumes here. I just need to know that we go down by a factor of 10. That's it. So the PV diagram process is what's being shown here. We are experiencing compression. Because we're experiencing compression, we are jumping to a higher isotherm. This is an adiabatic process. Volume drops, pressure goes up. We end up with a higher temperature at the end. We are dealing with air. Our gamma value is 1.4. If we need our CV value, again for air, 20.8. Adiabatic process, right? You got it right here. We got our two relationships that we care about here. There is a third one that would relate pressure and temperature. We don't need that one for this. We could use it, but we don't need it. So this is a matter of just rearranging these into proportions to figure out what the changes are going to be. So if I take my PV relationship here, I can divide by, I'm solving for P final here. So I'm going to divide by the volume, the final volume here, put them under the same exponent. So I got my ratio here. Now this ratio, right, it's initial to final. Okay, well that's, that's our 10 to 1 ratio there. So we were initially a lot bigger. So I could just replace this with 10. I mean, I put the numbers in there, but you could just put 10. The initial pressure is 1 atmosphere. I don't have to put this in Pascal, right? Anytime you have ratios or proportions, as long as you maintain the same units, you don't have to convert them to absolute ones, except for temperature. You do for temperature. But the other ones, you don't have to do that. Although if you did, it would never be wrong. You just doing extra steps in a problem, you're just increasing the likelihood that you make a mistake. That's all. That's the only fear with that thing there. Anyway, 10 to the 1.4 power, it's about 25. So the pressure goes up to 25 atmospheres. We do the exact same thing for the temperature. We can figure out what our new temperature is going to be. We have the same ratio. This is a different relationship. It's a gamma minus 1 value up here. So if I rearrange that, this is going to be 10 to the 0.4 power times my Kelvin temperature. You do need to use kelvins for these, right? That's always true. We end up with a higher temperature, which I'm going to convert back to Celsius because etiquette, It's 288 Celsius. Ooh, that's hot. All right? So that's great. And we want to know how much work's done in the process. Well, that's easy to do because Q is 0. So the change in thermal energy is the amount of work that's being done. Now, this is negative work, just to be clear, right? Because we're going backwards here, right? So that means there's, when this compression takes place, we're doing all right. So NCV delta T, I'll put my CV value in there. My N, I got to work out what that is. My initial parameters down here will tell me the number of moles that I have. So I have the initial pressure and volume and temperature, and I figure out my moles from this. And multiply all that together, we end up with 192 joules here. Okay, and so that work that was being done, this is negative, okay, because technically if Q is 0, this is a negative W here. The volume is dropping, so that work is being performed on our on the gas here, right? Okay, we end up with a higher temperature, because we have done this compression. All right. So 192 joules. All right, let's look at the last problem here. All right. Compression ratio of a diesel engine is 15 to 1. Great. Initial pressure is 1. Initial temperature is 300. Very similar problem. Find the final pressure and temperature after adiabatic compression. You might want to pause the video before you look at these answers and work this out on your own. These are in-class activities, and normally when it's not pandemic life, I actually have you work this out in class. That's not so simple to do over Zoom, so I don't require this anymore, at least while we're in this situation. But it would be a good idea to try to work this on your own before anything else happens, before you look any further. We want to know what the final pressure and temperature after adiabatic compression. All right, so this is a very similar problem. Very similar problem. We use the exact same relationships. We get a new pressure of 44 atmospheres. We get a new temperature of 886 Kelvin. We don't know how much work is done on the. Oh yeah, how much work does the gas do during the compression if the initial volume is 1 liter? All right, well, we got to put that. 1 liter is 10 to the minus 3 cubic centimeters. You need to have that in there. Now, we're using ideal gas law to find our moles, just like we did in the last problem. Everything's got to be SI for the ideal gas law, though. We don't have ratios or proportions here. This is a straight-up equation. 0.04 moles is the amount of gas that we're working with here. Put that all into our equation for work for adiabatic process, NCV delta T, and we end up with 495. Okay, so this was this is actually is negative again, right? Because this is the change in thermal energy is equal to Q minus W. There's no Q, so this is technically negative. Work is being done on the system here. Okay, so that's increasing the temperature. That's why the temperature is there. Okay, well, fantastic. That brings us to the end of this, and good luck on your exam that's coming up.